Hello, guys. Thanks for the invite. I am Professor Dimple Kumar Charlie Sejar from Virginia Military Institute, United States of America. Again, thanks for the invite, and I have very limited time to speak a lot in this conference. So let me directly start with the topic. So today I'm going to talk about the controllability of a neutral stochastic impulsive functional integral differential system by resolvent operator. So first of all, I just would like to give the introduction part and then the preliminaries. These are the two main important parts. And then after controllability result, because of the limitation of time, it's not possible for me to go through each and every step of the proof. So many things we are going to omit over here, but I would like to give you the main highlight of the proof. And then after the applications, whatever we are going to prove in the theoretical portion, that would be justified by the example. And finally, the conclusion. So that is a theme of this talk. So first of all, let me let you know the introduction portion. So what we mean by this one. So over the past few decades, the controllability is one of the fundamental concepts in mathematical control theory, and it plays the important role in both the deterministic and the stochastic control theory. So first, what we mean by the control system. Control system, that means we can steer the system from the initial stage, and we can give some input, some control, so that system hit the final desired state. So that's what we mean by the controllability. There are different notions of controllability, like stochastic controllability, null controllability, complete controllability. In the infinite dimension space, the same is referred as the exact controllability, approximate controllability. There are several notions. The new notion I just developed before a few years, that is called the trajectory controllability. Of course, we are not going to talk about here the trajectory controllability, but here our approach is slightly different. There is a stochastic controllability. And in the stock market, this type of controllability that is highly useful. A lot of applications are there based on this one. Our approach here, there is a resolvent operator as well as the fractional Brownian motion. So what we mean by the fractional Brownian motion? Fractional Brownian motion, I just would like to denote by FBM, b to the power h t belongs to r, is a Gaussian stochastic process which depends on the parameter that is called the Just parameter, HUR as a Just parameter h, lying between 0 and 1. And this stochastic process has self-similarity, stationary increments, and the long-range dependence properties. And this fractional Brownian motion is the generalization of the Brownian motion, and it reduces the standard Brownian motion when h equal to this, h belongs to 0 to 1. But if you take h equal to half, then this reduces to standard Brownian motion if h is equal to half. Fractional Brownian motion has attracted significant interest since the last few years, and that's why people are diverted to this one, the fractional Brownian motion. One more concept is there, that is the more generalized concept, the fractional Brownian motion, that is called the Rosenblatt process. We are not going to talk about here about the Rosenblatt process, but just the fractional Brownian motion. Recently, the existence, uniqueness, the asymptotic behavior of the mild solution of a class of impulsive neutral stochastic integral differential equations driven by fractional Brownian motion with delays have been studied. And several upcoming researchers are keen interest to study the solution or the solvation of the control problems in the field of stochastic system. And the controllability of the impulsive neutral stochastic functional integral differential system with infinite delay driven by the fractional Brownian motion, that is the main topic to be discussed over here. There are two types of delay. One is time delay, second one is state delay. We are going to talk over here about the time delay problem. And this time delay problem I have mentioned over here x suffix s, you can see over here xt. So it's both sides of the equality, we have a time delay in the system. So that's why it is called the neutral system. And time and state delay, this time delay, there are two types of time delay also. The one is finite time delay, another is infinite time delay. We are going to talk here about the infinite time delay problem. You must be wondering that what we mean by the time delay. Time delay, that means suppose we have some history, and suppose that history is a finite history. Suppose some fixed negative before a day, before a couple of days, suppose something has happened, and if you want to continue the same thing, and if you are looking for the desired result at that time, at that point you can start to give the control to the system and try to get the desired target. So this type of controllability that is called the finite delay control problem, but there are some infinite delay control problems too. As for example, suppose somebody goes to the doctor after the overnight fasting, and doctor says that doctor has reported last year when he went to the doctor has reported that he was not suffering from diabetes, but somehow that was in 2020, suppose November, but somehow in 2021 November, when he goes to the doctor just for the routine yearly checkup, and this time doctors report some diabetic problem. So at which time, nobody can predict this exact time when that diabetes entered to the body, when that guy has starting suffering from diabetes. So nobody can predict that. It could be before a month, before a couple of months, before 3 months, but nobody can predict exactly the same time. Nobody can say that on April 5th, 9 p.m., 20 minutes, 9 hours, 20 minutes, 9 p.m., and 3 seconds, the diabetes started in the body. Nobody can predict this type of things. So this type of delay part that is considered as the infinite delay portion. Lots of biological applications are there, stock market applications are, engineering applications are there, porous media applications are there based on this one. Lots of problems are based on this time delay as well as a state delay problem. Here our system that is described like this: d of xt equal minus gamma of txt equal to uxt script u minus gamma xt and b of ut. This b is a bounded linear operator, or script d you can say, and u is the control operator. This is the integral differential term. This is the nonlinear term, and this is the Brownian motion. This one is nothing but the impulsive term defined over here. System components are defined like this. U is the infinitesimal generator of a strongly continuous bounded linear operator T of T. You can say in our case, it's the resolvent operator in the Hilbert space X with the domain of and the OT is a closed linear operator on X with the domain of O that is contained in domain of U. BH is, as I told you, fractional Brownian motion which reduced parameter greater than half on the real separable Hilbert space Y. Control U denotes that takes the values in the L2 0 to T2U, and admissible control function for a separable Hilbert space. Script B is a bounded linear operator from U to X, and history, as I told you, the delay portion, infinite delay is over here, negative infinite to 0 to X, xt theta equal to X of T plus theta. And BH defined axiomatically. We are going to define this BH later on. And these all are the system components you can see over here. The impulse term 0 is less than T1 is less than T2 to T, xtk and tk minus represents the left and right limits of xt at time tk respectively. And delta xt, there's a jump in the state X at time tk. In stock market, sometimes you may have sudden jump, sudden fall, something like that. So that is considered as the jump, or you can say delta xk, and with I from X to X determining the size of the jump. Now, let me just give you some important tools which we are using over here to prove the control result for the fixed time interval 0 to T. I just would like to define the complete probability space that is given by omega script F and P, and BH, that is the, as I told you, set of Brownian motion with a one-dimensional Brownian motion and with reduced parameter lying between half and 1. And this B of B to the power H is center Gaussian process with covariance function defined like this, RH TS, that is equal to this one. And this BH is the following in a Wiener integral. You can see here, this BH is approximated by this Wiener integral, integration KH D beta S like this, where this beta is given by beta of T belongs to 0 to T is a Wiener process. So every fractional Brownian motion is approximated by the Wiener process. That's what I just would like to convey you. Whatever KH I have defined over here in the Wiener integral Wiener process, that is given in this term CHS to the power half, actually minus H. and 0 to t, and this one, where the ch is nothing but square root of h2h minus 1 and g of this one, and this g, whatever you can see over here in the denominator, that's the beta function, and this kh is nothing but kth equal to 0 if t less than or equal to s, and we denote some script h reproducing kernel Hilbert space of the fractional Brownian motion, and this script h is a closure of the set of the indicator function 1, 0, t belongs to 0 to t with respect to the product, inner product, this one, or HTS, that is defined in this form, 0 to t and 0s, like this one, RHTS. The mapping, all our mappings, of course, 1, 0 to t to BHT can be extended when isometry between the script h and the first winner chaos, and we will denote that one by BH and phi, the image of phi by the previous isometry. X and y be the separable Hilbert space, and L by x is the space of bounded linear operator from y to x. Q belongs to L, x, y be the operator defined by Q en equal to lambda and en with a finite trace. This is a definition of trace summation of lambda n that is finite, where lambda n is greater than or equal to 0 for all n set of natural number you can see over here, non-negative real numbers, and en is the complete orthonormal basis of y. Y is separable Hilbert space, and en is the complete orthonormal basis. We define the infinite dimensional fractional Brownian motion on the separable Hilbert space y with the covariance q as this form, BHT equal to BHQT, and that is summation of lambda n and then en and this one, where this BHBN, this one, this is the sequence, is a real independent fractional Brownian sequence of fractional Brownian motions, and this process is Gaussian. It starts from 0, has 0 mean and covariance, so that can be given like this in the literature. You can find the same thing. Well, now we define the inner integral with respect to Q fractional Brownian motion, and we introduced L20, another space that all Q Hilbert schematic process for functional psi from y to x, and we recall that psi belongs to this one is called Q Hilbert schematic operator. If this condition is satisfied, if this norm in L20 is finite, and that is equipped with the inner product, this one that is separable Hilbert space. The functional phi from 0 to t to L20 yx is a given function, and the winner integral phi with respect to this BH is given in this form, where this Bn, as I told you, is a standard Brownian motion. This Bn is a standard Brownian motion used to define the fractional Brownian motion, what we have seen in the previous case. I just would like to define now KH star, because we have now this phi. So we are defining all these terminologies for phi, our delay part, from H to L to defined by this one. And if you want to look at the proof of this one, that is given in this book. So I'm going to give the reference to. And for any phi in this script H, Hilbert space H, we have beta H phi is given in this form. So again, the same author, he says that H may not be a functional, but rather a distribution of the negative order. And in order to obtain the space of functions contained in H, we consider it in a product generated by the measurable functions like this, psi square equal to this one, and that is finite. My first lemma, you can find this one in the literature. If psi is from the interval to L20 yx satisfies this integral condition which is finite, then my previous equation 5, that is the well-defined and x-valued and a variable and estimates of norm of this one that is bounded by this integral condition. Here is the phase space we have defined, H from negative infinity to 0 to infinity, and L is defined like this, and we define the axiomatic phase space because delay portion that you cannot work with that delay portion with the usual Hilbert space or separable Hilbert space. You need to define some quotient space. So that's what we did over here. If you refer one of my papers from Jota, I think 2016, like this, and 2012 too. So I have proved this axiomatic Hilbert space, not for stochastic process, but already I proved this one, that you cannot work. People had been working with the phase space given by Hall and Kato. But I said that if you are working with finite delay, Hall and Kato phase space is okay. But if you are in the infinite delay, in that case, you cannot work with the Hall and Kato phase space, but we need to define some other space. And that is given by, that idea was given by Hino, Murakami, and Naito. And I picked up that line, and then after I generated another phase space, another new space. And that's what I have described over here for the stochastic process, right? This is just the extension of that work. So xi at ph, that is this is the space you can see over here, and this bh, that is equal to collection of all xi from -infinity to 0 to x. And for any t greater than 0, this estimation to the power of is bounded and measurable function on that negative part, and this integral condition is finite. And this BH, whatever we have defined over here, there is endowed with the phase, endowed with the norm, this one. And this is clearly a Banach space. You can consider any Cauchy sequence and try to prove the convergence of the same Cauchy sequence in the same space. So it's a complete nonlinear space, and it's a Banach space, so it's not that that hard. Consider the space B, D, I. D and I stands for the D stands for delay, and I stands for the impulse, given by B, D, I, that is equal to collection of all x from -infinity to x, such that x restricted to ik is in set of all continuous functions from ik to x, and right and left limit exist. They are equal for k equal to 1 to m. Like then these conditions are satisfied, and this x restricted on ik, actually is restricted on ik, that is in the interval this one, and the function, this norm, is a semi-norm in BDI. BDI is this one, as I told you, right? That is all the delay and the impulse, collection of all functions which belong to from the delay and the impulse, which satisfy the delay and impulse terminologies. So finally, that my delay portion, the whatever new phase space I have defined, that satisfies this inequality. And finally, I'm going to use my operator U and OT are closed linear operators on X, and Y represents the Banach space if equipped with the norm, graph norm, this one. And this notation stands for continuous function from the interval to the Hilbert space phi. And we consider the following Cauchy problem like this. And this Cauchy problem, I just would like to give you the mild solution of this Cauchy problem in terms of the resolvent of an operator. My resolvent of an operator definition is like this, that R0 is equal to identity operator bounded by the exponential function. And for each x in X, RTX is strongly continuous. And for this, RT is from set of all intersection of set of all continuous function and continuous functions. And then R dash T that is given in this form. And now, if these two conditions, H1 and H2, that is C0 semigroup, U generates script A, you can say generate C0 semigroup, and for all T positive, 0T is a continuous linear operator from Y into X. And moreover, the function C, such that this condition, that is from the Sobolev space, belongs to this Sobolev space and satisfies this inequality. So if these two conditions are satisfied, then there exists a unique resolvent operator of the Cauchy problem given over here. And my another lemma, that is, of course, both of them, they are given in the reference 5. For t greater than 0, there exists a control constant L such that this condition RT plus sigma epsilon or R epsilon RT, that is bounded, that is this is not equal to L epsilon. And in a sequel, we recall some existence of solution of the following integral differential system. And the continuous function x from 0 to infinity to x is said to be strict solution of the equation if these two conditions are satisfied. And again, if in the previous slide, H1, H2 hold, if x is strict solution of equation 8, this equation 8, then the following formula, that is called the variation of constant formula, and this formula hold. So just now you can say this x dash t to xt, that means this is the mild solution in terms of the resolvent operator of the Cauchy problem. And accordingly, using that mild solution of a quasi problem, using the resolvent operator, I have just given the mild solution for our system, our impulsive delay system. So I just give the mild solution of the system, and that is given in this form xt. And I would like to assign one operator over here. So before I start this one, I just would like to give the definition that 0 to x called the mild solution if x satisfies the variation of constant formula. And another definition is let V is bounded, closed, and convex subset of Banach space X, and let pi1 and pi2 be 2, just the operator, you can say. V into X satisfy pi1 X and pi2 that belongs to V, convex Banach space, be convex subset of Banach space X. Pi1 is contraction, that means all my linear portion will go with this operator pi1, and completely continuous my non-linear portion I just would like to keep with pi2. That means this operator pi2, that means I can prove the complete continuity of that non-linear portion. If that is possible, in that case, there exists a z in V such that z is equal to pi1 plus pi2. So this combination, this direct sum, that is nothing but z. And we require this definition. This is the control definition. Already I explained to you this control definition. Control definition varies from system to system. And here we are also going to see, I have, I think 7-8 minutes left out. So let me continue. Let me continue with this assumption. So this is the control definition. System is said to be controllable in the interval negative infinity to t if for any initial stochastic process phi defined on negative infinity to 0, my delay part, there exists a stochastic control u in L2 0 to t to u, which steers the system to the initial stage phi to terminal stage x1 in 0 to t time period t, such that the mild solution x dot xt satisfies xt equal to x1. So final time and target is achieved, where x1 and t are the pre-assigned terminal stage and time respectively. I require a few more assumptions like this resolvent operator is compact and there exists m such that, there exists m such that that condition is satisfied. You can see over here, R square is bounded. There exists constant gamma r such that the mapping, this one satisfies this estimation of this, that is less than equal to this one, kind of which is continuity. And mapping this from BH, whenever BH is there, that means just make sure that that is through that is because of the delay part. And the non-linear continuous function t is a measurable for each x in BH. The function t to gamma tx is almost everywhere for t belongs to 0 to t. There are a few more assumptions over here. My impulse condition also satisfies the Lipschitz continuity and function sigma from 0 to infinity L2 y2x satisfies this integral condition, and that is finite. And control function, that means we have to have the operator w from u to x defined by w equal to 0 t rts bus ds. Why this one is required? All control theorists they know this thing. So this w operator w is an invertible inverse operator w tilde inverse in the quotient space like this, and kernel of w that is given in this form. Suppose all my assumptions hold, then the system is controllable, provided this condition is satisfied. This is less than 1, actually. This is less than 1. You can consider 1 here. Okay, so for this particular system, mild solution, I have defined the control in this form. And you can see over here, this is the invertible operator W, and that's the reason that I assume that the invertibility of the operator W like this, so that I can have, because I would like to extract this ut from this one. So that's why I require the invertibility of the operator W. Anyway, so this inverse of this one, this ut is defined like this. And now this control ut is the stochastic control of my data system, and obtain the nonlinear operator psi on BDI, delay and the inverse impulse problem. It is clear that to prove the existence of a mild solution of the equation is equivalent to find the fixed point of the system. So I just would like to decomposite my space xt equal to zt plus yt, and it is obvious that x satisfies a stochastic problem system 10 if and only if z satisfies z equal to 0 and the mild condition, mild solution like this, z equal to this one. You can see over here, I've just plugged the value of b of ut that is in this form. Okay. So my control u for this z of ty, you can see here my control zt equal to like this. This is my mild solution. This zt is given in this form, but you can see z plus y. So now it's not xt, it's zt, z plus y, z plus y. So accordingly, I need to define my control also in terms of z plus y. It's invertibility of the operator w, and I define my control like this. And b di0, another subspace of bdi. Collection of all z's in BDI such that z is equal to 0. And that subspace, that Hilbert space also satisfies this norm. Equipped with that norm, you can say. And now we define the operator theta from BDI0 to BDI0 such that theta zt, that is given with this one. You can see over here. And BK is this one. BK is contained in this bounded closed convex set. Zt plus yt is bounded by this one estimation of uz plus y square is less than or equal to this one. Let me just, this is just a mechanical step, so let me skip this part. And finally, I ended up with z1t. You can see over here that I have all my linear portion over here, and my non-linear function that is associated over here. I kept it over here with theta 2. So not pi 1, pi 2, I just change a simple theta 1 and theta 2. Theta 1 plus theta 2 must belong to BK. Theta 1 is a contraction, theta 2 is a continuous and compact map. So actually it is equicontinuous, not continuous and compact. I would say it's equicontinuous. So uniformly continuous, compact. Then these three conditions are satisfied. That means we can say that z equal to, or theta 1 plus theta 2, that has a fixed point. Okay, so estimation of this one is greater than 0, and that is greater than k. We want to prove that we have to show that there exists some k greater than 0 such that theta 1 plus theta 2 belongs to this one. And if it is not true, suppose this is not true, in that case there exists k greater than 0 such that this condition is not satisfied. So we have this estimation. We start like this, and finally we say that we claim that after all our assumptions, we claim that our assumption is wrong, and that's why there exists at least one k like this. So dividing both the sides by k, and finally you ended up with these conditions. These are just mechanical steps. My second part is theta 1 is a contraction. So this is the contraction mapping. You can see over here, I put the contraction. My third part is theta is a completely continuous operator. Completely continuous, that is a uniform boundedness and equicontinuous. So, and by Arzelà-Ascoli theorem, it's a uniform bounded and equicontinuous. That means that is nothing but the compact. So in infinite dimension space, compact implies closed and bounded, but closed and bounded does not imply compactness, and that's why we need to rely on the Arzelà-Ascoli theorem. So theta 2 is completely continuous operator. So I just try to prove like this is continuous. I mean to say it's equicontinuous always, please. So I just took one sequence, and it's a very straightforward proof. So I proved that estimation of theta 2 z to the power and theta 2 z and square, that is given like this, and finally that tends to 0 as n tends to infinity. So theta 2 is equicontinuous, or theta 2 is continuous. Theta 2 maps BK into equicontinuous map. So I proved that part over here too. And then after finally theta 2 BK is pre-compact in this set. Pre-compact I have proved over here. So altogether we can say that my last equation, that is a compact, the compactness of the RT. And therefore we can say that whatever the space estimation of this one, that is less than or equal to this one, and so V epsilon T is pre-compact in X. And finally, we have proved like this that estimation of this one tends to 0 as sigma tends to 0 plus. And there are pre-compact sets arbitrarily close to the set Vt, and hence Vt is also pre-compact in S. Therefore, by Arzelà-Ascoli theorem, theta 2 is compact, as I told you. And that's why by using Krasnik Krasnow-Salsky fixed point theorem, there exists a fixed point z for theta k upon bk. We define xt equal to zd plus yt. And it is easy to say that xt is a mild solution of one that is satisfying the condition. So now the application, first order equation, let me just consider the heat equation over here. BH2 is a cylindrical fractional Brownian motion. You can see over here, I just try to match all these terminologies with my given system. And phi is given continuous and stochastic process such that phi square is bounded, and we take x equal to y equal to L to 0 to pi. Domain of A is nothing but collection of all y in x such that y is absolutely continuous and y double is in x, y0, y pi equal to 0, 0. My interval is nothing but 0 to pi over here. You can see my interval is 0 to pi, and ax is given by summation of square that's within our product. En is square root of 2 over pi sine of 2x, and norm of this one, hx, that is e to the power 4s. This is orthogonal functions. And the phase space hx is like this L, whatever I define, that is given like this, one force is finite. And the phase space BH, the Banach space, like that is defined like this. So just accordingly, you can just proceed further and just try to match all the conditions, assumptions, H1 to H8, whatever we have done in the theoretical portion, you can match all these conditions over here. And that's what I did over here. I'm sorry, because of the limitation of time, I need to conclude. And finally, my conclusion is, in this work, research work, we have proved the controllability result of impulsive neutral stochastic functional integral differential system driven by fractional Brownian motion with infinite delay in a real Hilbert space, separable Hilbert space. The controllability results are obtained using the stochastic analysis, Krasnow-Salsky fixed point theorem, and the theory of resolvent operator in the sense of Brimmer. The practical example is provided to illustrate the viability of the abstract result in this work. We will consider the controllability of the fractional neutral stochastic system driven by fractional Brownian motion in the future work. Resolvent process, that's the future work. State dependent delay, infinite delay, that's the future work. Numerical estimation, that's the future work. So lots of work. You can generate the same result in a lot of different ways. And these are some references I have used to prepare this result. And thank you so much. So thanks for the invite again, and looking forward to seeing you next time in person. Thank you. Thanks for the invite.